Hi, I'm Abdullah Hamdi, and I'm going to present our ECCV paper, AdvPC, Transferable Adversarial Perturbations on 3D Point Clouds. This work is from our AdvPC group at KAUST, led by Dr. Bernard Ghanem. 3D point clouds are an efficient way of representing 3D data, and it is widely used in applications like self-driving cars. Deep learning has been successfully applied on 3D point cloud data on a variety of tasks like 3D classification and segmentation. The 3D deep learning success is largely attributed to the success of PointNet and its subsequent variations. And more recently, the graph convolutional networks like DGCNN and its variations. On the other hand, 2D CNNs are known to suffer from the phenomena of adversarial attacks. By adding small noise proportional to the gradient of the loss with respect to the input, the resulted unnoticeable additive noise can make the trained CNN misclassify the adversarial image. 3D deep models have also been shown to suffer from adversarial attacks, starting from this work by Xiang et al. From CPR 19. But these attacks are shown later to be easily defendable, and they don't transfer to unseen 3D networks. Another work from CPR 20 by Tsai et al. Used the Cannon laws to create smooth attack that can be 3D printed while remaining adversarial. But still, these attacks are specific to the victim networks and they don't transfer to other networks. The defense by Zhao et al. From ECCV 19 showed how it is easy to defend against previous attacks with simple statistics like random sampling and denoising. We propose a new adversarial attack on point clouds that transfer to unseen networks and break available defenses, making the 3D attack more dangerous. Our contributions are twofold. We propose a new attack pipeline allows to generate transferable attacks, and we achieve high transferability and beat state-of-the-art on breaking defenses on ModelNet 40 data. Here, we show our attack pipeline. In order to attack the victim network, we optimize an additive perturbation that will be added to the clean point cloud to create an adversarial point cloud. In addition to the regular adversarial loss in our optimization, which is used by the baselines, by the way, we utilize a pre-trained point cloud autoencoder to create a data adversarial loss that is tasked to fool the victim network even after reconstruction with the autoencoder. By balancing the two losses, we successfully attack the victim network and generalize the attack to unseen networks. If we have a closer look, we can see the perturbation effect on the point cloud. Our main objective makes the perturbation as small as possible under some LP norm, while satisfying the fooling criteria of the classifier to incorrect label T prime, and the fooling criteria of the reconstruction of the autoencoder of the perturbed sample to an incorrect label T prime prime. We formulate our objective as hard constraints and solve by projected gradient descent in L2 and in L infinity. This is the adversarial loss followed commonly in the literature. Gamma is a hyperparameter that trades off between regular adversarial loss and data adversarial loss. Epsilon P is the norm budget, which is the maximum allowed LP norm in the attack. Here is the full objective with the pipeline. The objective can be minimized iteratively with gradient-based methods. Here, we show the optimization update step for the perturbation variable with the projection function on L2 sphere with some L2 norm budget epsilon 2, or with the projection function on L infinity sphere with some L infinity norm budget epsilon infinity. The data used in our experiment is ModelNet 40. The networks are PointNet with its two versions, and DGCNN. We use AdvPC with standard learning rate and 200 optimization steps with two different initialization steps. Here is an example of successful AdvPC attacked point cloud. Here we show different examples of targeted AdvPC attacks. The black point clouds represent unperturbed point cloud, while the blue are the attacked point cloud. The prediction of each network is shown under each attacked point cloud, which matches the target of the attack. Here, we show untargeted AdvPC attacks. We show our transferability results with reported success rates of the attacks. Each big row is the victim network with our attack benchmarked against other baselines. The evaluation is performed against all networks, including the ones that are not seen during the attack. 2 epsilon norm budgets are shown in this table. Please note our method is strictly better on transferability results, highlighted on off-diagonal values, compared to the other 2 methods. And with big margin in DGCNN transferability, with improvement close to 40%. Even for different epsilons, we still outperform other methods in transferability. Here, the attack is by DGCNN, and our method success rate versus norm budgets, plotted in green, outperform other baselines. Here we show all the results across all networks and all norms. We can better visualize these plots by averaging all the success values across the norms and plotting transferability matrix for each attack method. Bright diagonal indicates attack success on the victim network, while bright off diagonal indicates better transferability to unseen networks. By averaging the off diagonal values for each matrix, we obtain a transferability score for each method, which summarizes an overall transferability. Our method performs better overall on transferability. Here we show the attack success rate under 3D defenses when attacking DGCNN. We beat the baselines on breaking defenses and by up to 38% improvement on some defenses. We observe similar improvement against defenses when attacking all the other networks. We plot success and transferability against different values of our hyperparameter gamma. As gamma increases between 0 and 1, success drops and transferability varies. We pick gamma equals 0.25 to balance both success and transferability. Furthermore, we observe intrinsic sensitivities for different 3D architectures. Different networks behave differently under adversarial perturbation. DGCNN is the most robust network in general. Here, we study the effect of the autoencoder. The autoencoder used in AdvPC does not affect the unperturbed point clouds, but clean the baseline attacks, which means it recovers the correct class label, which is toilet in this case. And hence, the autoencoder is a good defense in itself, which explains the success of our method. On the other hand, AdvPC attack fooled the classifier before and after the autoencoder. The autoencoder is misled to convert an attack toilet to a chair instead of recovering the correct shape as the other attacks. In all the previous experiments, we showed only L infinity results. If we used L2 as the norm constraints, we get the following transferability results, which also show the superiority of our methods against the baselines. Please check our paper and the code for more details. Thank you.